Good afternoon, everyone. As Andrea said, my name is Tamara Griffiths. I currently work as a research associate within the radiochemistry team of NNL, based at the central laboratory, which is located on the Sellafield site. And I've been in that position for about 3.5 years. And today I'm going to talk to you about how lasers can be used to study the nuclear fuel cycle. So when I'm talking about lasers, I'm talking about laser-induced luminescence spectroscopy. And this is the renewal and development of a UK unique tool to study radioactive samples. And luminescence spectroscopy is a very powerful tool for determining the speciation of radionuclides. And speciation is knowing exactly what chemical species exist under certain chemical conditions. So in this talk, I'm going to be talking about the americium ion, as that is the ion that we can currently study using this technique. But in the future, what we'd like to do is expand the capability and move on to other ions such as uranium. So I'm just going to talk about some basic principles of luminescence, what the technique is built on. So what is it? When light energy is applied to a molecule, it can cause an electron to be excited from a ground state to a higher energy excited state. And when that electron relaxes back down to the ground state, it has the potential to release energy in the form of light. And what we can do is that we can detect that light emitted and use it to our advantage. So specifically for the americium ion, what we do is we apply laser energy tuned to 503 nanometers to promote the electron within the americium ion. And we detect energy, the light emitted at 691 nanometers when that electron relaxes. So this is an example of some of the spectra that we've obtained using luminescence spectroscopy, studying the americium ion. And each spectrum that you see here is taken at a different time delay from when the original americium species was excited. So as you can see that over time, the intensity of the light emitted from the americium ion decreases. And what we find that when we look at that intensity, it decreases exponentially and on the nanosecond time scale. And the information that we can get from spectra like this is a function called the luminescence lifetime, and that is a measure of how long the excited americium species lives for. And for americium, that is on the order of nanoseconds. And every chemical species has its own individual luminescence profile. So and it's a little bit like that chemical species having its own fingerprint. It's unique. So what information can we get from luminescence profiles? We can get information about what the americium ion is coordinated to. And I'm going to talk in the terms of ligands. And a ligand is a molecule that has the potential to bind to a metal ion. So the middle person that you see here is the americium ion, and the people who are surrounding it would be ligands. So those ligands can be solvent molecules, such as water. They can be organic ligands containing carbon, or inorganic ligands which don't contain carbon, such as nitrate. We can also get information related to the stability of complexes. Some complexes are more stable than others, and we determine the stability as a function of a stability constant. So one of the main advantages of luminescence spectroscopy is that it has very low detection limits compared to other spectroscopic techniques. So when we're looking at a chemical species using luminescence, if we gave it an arbitrary value of 1, to then study that chemical species using absorption spectroscopy, you'd be looking at about 100 times the amount that you'd need, and for NMR spectroscopy, about 1,000 times the amount. So here is a very general diagram of the nuclear fuel cycle. We've got the mining of the ore, enrichment into manufacturing the fuel for use in a power plant, after which the spent fuel will undergo some interim storage. Separation processes will occur to recover the useful elements to manufacture into future fuel. And some of the waste products may be directed into a geological disposal facility. So over the next few slides, I'm just going to talk about how luminescence spectroscopy could be used to tap in to certain elements of the nuclear fuel cycle, to understand what chemical species can exist, and that's key for optimizing of the fuel cycle. So when it comes to storage, a good example are the nuclear legacy waste ponds based on the Sellafield site. This is a very complex chemical system. You've got spent fuel in there containing many radionuclides, such as the americium ion. And these ponds are open to the environment, so what you get is you get carbon dioxide dissolving into the ponds from the atmosphere to make carbonate ions. We've also got plenty of hydroxide in there, as the ponds are about pH 11. We've also got organic ligands, and this comes from the dead plant and animal matter that can fall into the ponds and decompose to produce ligands complex to their radionuclides. And there's also thought to be a nuclear waste sludge present, which is thought to be composed primarily of brucite, which is a magnesium hydroxide decomposition product of magnox cladding. So all these different factors can influence the speciation of metal ions in the ponds. So some previous work that we've done, we've tried to chemically model these ponds. We took the americium ion and we complexed it to a well-known organic ligand called EDTA, and we looked at the effect of carbonate and hydroxide on that complex, and we got information related to speciation over a pH range, and also we got information related to the stability of those complexes. And that information can be used and applied to look at the ponds, trying to understand what chemical species might be in there and help with the cleanup. Another area that luminescent spectroscopy could be used is with advanced reprocessing. And this is looking at the separation of minor actinides from spent fuel, which has many advantages, such as it can reduce the heat load and radiotoxicity of nuclear waste. And also, as Zara spoke about earlier today, that if we can separate americium-241 from aged plutonium, then we can convert it into a product that could power future space missions. So at NNL, we have led the separation technology of americium from plutonium, and we've done that using a ligand called TODGA. And using luminescent spectroscopy, we've investigated how the TODGA ligand complexes with the americium ion, and what we've determined is that 3 TODGA ligands can bind to the americium ion. So some next steps for the use of this kit. We've had a PhD student come to visit from the University of Oxford, and she's been involved with in a collaboration with us. She synthesized this ligand on the left-hand side as you look at it. This is a cyclone derivative, and she synthesized this as a potential separation ligand. She came to see how her ligand interacts with the americium ion using luminescent spectroscopy. We've also been involved in a collaboration with the CEA, looking at this potential separation ligand on the right as you look at it, which is a sulfonated BTP. And again, we've been looking at how that ligand interacts with the americium ion using luminescent spectroscopy. This piece of kit is now also part of the NNL-led FLAME research group. And this research group comprises many different laser pieces of kit, such as laser-induced breakdown spectroscopy and also Raman spectroscopy. And collectively, they will help with the characterization of chemical species within the nuclear fuel cycle and help to optimize the process. And if you haven't seen already, there is a FLAME demonstration area as well that you can go and visit. So as I've spoke about earlier, what we'd like to do is expand the capability. So in another body of work that I've been involved in is that I've set up, or helped to set up, a new capability where we can grow bacteria in an aseptic and anaerobic environment. And these bacteria are important because they occur naturally in the environment, and they can reduce uranium in the +6 oxidation state to uranium in the +4 oxidation state. And this is important because uranyl-6 is very mobile in the environment, whereas uranium-4 is not, it's less mobile. And on the pictures here, uranyl is the left-hand picture, it's a yellowy colour, and uranium-4 is on the right-hand side, it's a black precipitate. So what we'd like to do is use luminescent spectroscopy to study uranium in this biogeochemical process. And this has importance when it comes to geological disposal facilities. It's thought that these bacteria could provide a natural containment barrier to help prevent the migration of radionuclides in the environment through them being less mobile. So I'd just like to thank everybody involved with the renewal and development of this capability capability at NNL. And also, hopefully today I've shown you how luminescent spectroscopy is a powerful tool for characterizing chemical species. Potentially it can be of use in your work in the future. Thank you very much.